that brings us to the most important topic of this particular course, which is stability, right? So if we are controlling a system, right, this word stability is used by many people, and in a very different context, and sometimes different people use it with very different meaning. So what are the various possibilities that we want as a person who is controlling this particular system? Forget about the definitions that I have gave so far, but say if a layman uses the word stability, right, what could that person mean, right? As we just saw, in some cases they mean things are kind of under control, bounded. Okay. Now on the other extreme, basically people believe that something is stable simply means equilibrium behavior. Okay. So that means if I am at that particular point, I'm going to remain at that particular point forever, right? So that's also sometimes people use it as stable behavior. There are other notions. Basically, if I have a system, right, and I'm keep on getting perturbed by some noise, right? Imagine basically you are driving in a road and you're sitting in the car, and then the road profile is not smooth enough, and then that's the noise that we are getting. The vibration that we get is, we can call as output. So one can think of basically if the noise is bounded, then the output, the vibration we are experiencing, should be bounded. So that's also considered as stability, and then controls experts gave that name as bounded input, bounded output stability, right? And we will go through this notion briefly. It's interestingly, for linear systems, most of you are familiar with basically models where this block diagram is denoted by some kind of transfer function, and you have an output. We define bounded output, bounded input stability as something like basically norm of y is, let's say, less than equal to some constant times the norm of input, and then this constant we want to kind of minimize, right? So that's a typical control problem, and there could be many other specifications for control problem, but typically in an undergraduate course, that's what we focus on. And then this g of s is a transfer function, and typically ratio of not necessarily always, but let's say some kind of polynomials. Some of you may remember the details in terms of basically we kind of assume that the numerator will have at most the same order as the denominator, and there are reasons for that. The nice thing is, for such systems, basically one can actually write a state space model of the form x dot equals ax. So what we are doing here in this particular course is kind of a generalization, and this kind of modeling can never model nonlinear systems. Is purely linear system. So but then we've been dealing with these kinds of linear systems in this particular course. In reality, such transfer function has an equivalent state space model, and then there's not one single state space model for a given transfer function, but there could be multiple, and some of those things you would typically learn in linear systems, right? So it's not like we are doing this alien kind of system, right? So you'll have the x dot equals ax plus bu, y equals cx, as opposed to simply x dot is equal to ax is what we've been doing it. So here again, this nice bounded input, bounded output stability definition can be applied to the state space model also. But one of the most interesting results is basically Bibo stability. The bounded input, bounded output stability is equivalent to the Lyapunov and asymptotic stability. Okay, well, actually not asymptotic, not Lyapunov, but more asymptotic stability notion, right? So in that sense, this powerful result for linear systems actually kind of tells us that we can live with asymptotic stability notions, and then we can guarantee Bibo stability and so on. But unfortunately, this is not necessarily true in nonlinear systems. So one has to look at these notions carefully apart from this asymptotic stability. So you have many such notions. The simplest of them is boundedness, and then other extreme, which is not such a great definition, is basically this steady state or equilibrium behavior. But what we are looking for is even people, let's say they use the word stability to say something like a particular element is going to be stable. You know that a lot of these radioactive elements and things like that, they're not stable. You can artificially create them in the lab, but they're never stable, and then perhaps you are aware that they end up becoming lead at that particular point by just it may take millions of years in some cases, but they will lead to some more stable element. So what does it mean? If you perturb something, basically can you go back to that particular state is basically what we can think of as stable behavior, right? So but strictly speaking, all these are possible valid definitions, and then one has to be careful in terms of basically if you are interacting with some person who is doing an application, one has to understand which behavior are they really looking for and appropriately apply the methods that we are learning here. So in the case of equilibrium behavior, we denoted two kinds of notions, right? Lyapunov stability and asymptotic stability. Okay, so Lyapunov stability is something like this. Loosely speaking, start close, stay close, right? It's very imprecise in terms of what that says, but a slightly better way of using the English is basically if I want to remain in a small neighborhood around the origin, can I find a neighborhood, smaller neighborhood of course, close to the origin, so that if I start within that smaller neighborhood, will I remain in the bigger neighborhood that I chose, right? And then that first neighborhood, the bigger neighborhood, let's say I'm choosing this neighborhood, right? And can I actually find a smaller neighborhood where if I start somewhere here, I'm going to remain there, okay? Perhaps I can go back, but I'll remain within this thing, right? So such notion is called Lyapunov stability, okay? And I mean, this has been always the case, right? Things like concepts like continuity, limits, and things like that. Intuitively speaking, they are quite easy to understand, right? Something limiting, you can see a bunch of examples, sequences converging to a limit point and things like that. As soon as we want to make that rigorous, and you will end up with very complicated definitions. And in fact, the definition of limits and later calculus in terms of derivatives and things like that, that depend on the definition of limits and things like that, continuity and all those aspects have existed long before people came up with the definition of rigorous definition in terms of these epsilons and deltas. And then in fact, when the epsilon delta definitions came, basically there was a serious division in mathematicians, and then many people felt that this is a useless kind of exercise, but eventually all of them died or lost out or converted to and agreed that epsilon delta definitions are the most precise way of defining whatever we are trying to define. So Lyapunov stability is kind of that extension of continuity of functions at a particular point to dynamical systems in terms of talking about basically how a particular equilibrium behaves, right? I mean, don't think of it as a purely continuity notion, but it's perturbation of an equilibrium, what happens when you perturb the solution, whether it will remain close to it or not. But the word close and small and big and things like that are imprecise, so we have to introduce the nasty epsilons and delta definition, right? So Lyapunov stability is the most complicated thing that one has to understand. But once we have Lyapunov stability, let's say I start here and then I may roam around, and then can I actually get back to the equilibrium point? Can I get to the equilibrium point? Wherever I start, perhaps I may roam and then, but never stay bounded within my original neighborhood, and then I can reach the equilibrium point. Such a notion, basically, you have this basic bounded notion of Lyapunov stability. The difference between boundedness and Lyapunov stability is you can actually demand the neighborhood in which you have to live, and then that's the Lyapunov stability. But if we add convergence, if all the solutions are converging to a particular equilibrium point, along with this additional behavior of stability, we call that as asymptotic stability. Okay. So, and then of course, typically this notion is local, right? That means only in the neighborhood of this equilibrium we can guarantee such behavior. But one can imagine that in some cases it's going to be global, in the sense that wherever you start, you are going to converge to the equilibrium point. So only the convergence part, we are talking about obviously global. So if you have globally convergent solutions along with your Lyapunov stability, then we call it as global asymptotic stability. And the third notion that we discussed and we keep referring is basically exponential, right? Exponential stability is quite simple to understand. It's essentially same thing as asymptotic stability, but the convergence rate is much faster and it's exponential and things like that. So again, you'll have both local and global notions, right? So ideally speaking, if I'm going to control a system, I would like exponential stability as my final outcome, but in many cases that's impossible to achieve, and then we have to live with weaker notion of asymptotic stability, right? So let's formally summarize what I just said. Basically, this is zero solution is Lyapunov stable if for every neighborhood of 0 there is a neighborhood of 0 such that the initial conditions in the second neighborhood admit solutions in the former neighborhood. It doesn't go beyond the former neighborhood. You can guarantee that the solutions don't go. And the zero solution is asymptotically stable if the equilibrium point itself is Lyapunov stable, but there is some neighborhood. If you start there, I'm going to converge to the equilibrium point, right? And all these neighborhoods can be very different from one another. But the zero solution is exponentially stable if it is asymptotically stable with the exponential rate of convergence, right? And the zero solution is globally asymptotically stable and respectively globally exponentially stable if it is Lyapunov stable and the solution converges to 0. If in addition, if the rate is exponential rate, then we call that as globally exponential stability, right? So, these are the notions, and quite complicated to even prove it through simulations, right? Why do I say that? Even in ideal case where we know that the solutions exist everywhere and things like that, to check for Lyapunov stability to start with, I'm going to give you a neighborhood, and can you actually give me a neighborhood so that I can guarantee that it remains in this thing? Well, every neighborhood, technically speaking, has infinite number of initial conditions. In fact, more dramatic way of saying it is you have uncountable infinite number of initial conditions, right? So no computer in this world is big enough to actually simulate uncountable set of initial conditions, right? There's a big talk of quantum computing trying to solve many of these things in a different way, but I'm not sure if even quantum computing can address such a uncountable initial conditions, right? So that's it. Nobody can verify Lyapunov stability using numerical methods, and the same thing goes for asymptotic stability and exponential stability. What one can show through numerical methods is basically demonstration. One can see that, okay, fine, I'm convinced that this is Lyapunov stable, and I see that that is kind of demonstrated on a few initial conditions. So then where do we end up? So how can one actually show a particular equilibrium point is Lyapunov stable? Well, one way of doing it is actually you can solve it analytically. You'll have an expression in terms of time, right, for the solution x of t, and then check this particular definition. You bring these epsilons and deltas and things like that. It's going to be a mess, right? Except linear systems, most of the other systems are going to be quite difficult to solve, right? And if you count all the number of ODEs where we can have an explicit solution, they are like basically minuscule or zero measure compared to, say, all the ODEs where we don't have any solution, right? I'm not talking about numerical solution. Numerical solutions are approximate and they're there, but for certain initial conditions we can solve and things like that, and that too they are approximate. But I'm talking about explicit function form is only available for handful of ordinary differential equations beyond linear systems. Given this difficulty, therefore, this definition is almost useless if we want to check it just through definition, right? So Lyapunov, the mathematician who discovered the notion of stability, who defined the notion for us, also provided the solution, and that's the power of this particular method. So how do we do this? Well, I mean, this is the beauty of Lyapunov function theory, right? We don't really want to solve the equation, because solving doesn't help. Most of the time we cannot solve for an explicit form, but even if we solve it, then getting into the epsilons and deltas is a nightmare. So is there a simple way of actually avoiding all these things, and just using the function f, can we do something? And Lyapunov had this fantastic idea. It kind of inspired from physics, right? In physical systems we have this energy that is typically, let's say if you have a mechanical system, you have positions and velocities, and then the total energy is going to be sum of potential and kinetic energy, and that energy will never be negative. They'll be typically, depending on where you put the sort of what do you call base point or datum, and one can define a positive definite function which is energy function. Then the energy dissipates in reality. In real world, basically you cannot create energy if you have if you have a system where there is no external input, and that system is going to remain in a nice possible fashion in terms of its trajectories and things like that. So that was the idea. Mechanical systems have this natural tendency to reach an equilibrium point, or even if it doesn't reach an equilibrium point, it remain in a particular bounded region because of this particular fact. You cannot have infinite amount of energy in a system that does not get any input from outside, right? So using that particular idea, then our great mathematician Lyapunov defined this Lyapunov function for a very general ordinary differential equation. To start with, we defined something called Lyapunov function candidate. It's simply v of 0 is 0, and then v of x is positive for all non-zero, right? And then we call a candidate to be a Lyapunov function if it satisfies, sorry about the typo here, that's v dot, dot on the top of v, if it satisfies this v dot less than equal to 0. So the energy is kind of always decreasing. There's going to be dissipation, where v dot is basically defined as this what you call gradient, and we, in this particular course, we chose to represent gradient as a row vector and f is a column vector. So if you take the inner product of these two, we get the v dot. That's the definition of v dot, and if that happens to be less than equal to 0 for all x, right, not x not equal to 0 but for all x, then we call that as a Lyapunov function. What more is, basically, if that's satisfied, then we can conclude something about stability. But let's go on with the definitions. If you recall, basically, if this function v is going to satisfy one more condition, like if v of x is going to go off to infinity, as x tends to infinity in any direction of the space, then we call that Lyapunov function as radial and bounded, right? If you chose a function which is radial unbounded and it has some kind of global minimum and things like that, and that doesn't happen to be 0, then you just shift it and make it a Lyapunov function, right? So even if you have an energy function that is not 0 at your equilibrium point, you subtract the base energy and then you'll get the Lyapunov function, right? So what can we do with all this? This, as you can see, except this v dot part where we have f, nowhere else we have f. So that's the nice thing, it depends on f kind of loosely, right? So what does this tell us? Well, the main fundamental theorem of Lyapunov, this is actually called as Lyapunov's direct method or second method. If you have a Lyapunov function v, right, that means it satisfies v of 0 0, v of x is positive for all non-zero x, and then this derivative gradient in the product with f is less than or equal to 0, then we can conclude that 0 solution is Lyapunov stable. And typically, these conditions have to be satisfied in a neighborhood to get the local notions, and if you want global notions, not that the Lyapunov stability is a global notion, but if you want asymptotic stability globally, then we have to satisfy additional conditions, right? So if v dot part is strictly negative for all non-zero x, then we can conclude asymptotic stability, and couple of other conditions are satisfied, then we can get exponential stability. And if v is radially unbounded, it's a very technical condition. If once we have radial unbounded condition, what happens is basically we'll get these nice if the level sets, sub-level sets, v of x less than or equal to some constant will always be nice closed and bounded. If we don't have this radial unbounded case, then we'll have examples where things run off without being bounded, right? So in the global stability conclusion, basically we need this radially unbounded condition. Again, that's not kind of a necessary condition, but that is a sufficient condition. So we have these nice results, right? Again, I want us to be amazed by this particular result. We have said this before. The original definition, there's no other way of defining stability when we have this epsilon, when we have this close, start closed, remain closed, and things like that. There's no other way but to use this epsilon delta, right? And this definition is going to be in terms of the solution, and which is very difficult to achieve. Instead of trying to solve, we will actually sort of make the problem abstract, and then basically imagine that this function exists and satisfies these conditions that are easy to verify, right? Well, easier said than done, but it is at least possible because it's just a verification of some function rather than depend on some solution that we don't have. And that's the power of this particular method, right? So the nice thing about this method is, are you looking for Lyapunov functions in dark? Absolutely not. I mean, basically the converse results of Lyapunov say that there always exists Lyapunov functions such that something is true, right? You don't have converse necessarily for everything, but for certain exponential stability, asymptotic stability, one can actually have a converse theorem. But unfortunately, converse theorem doesn't provide an algorithm to construct, and that's the biggest difficulty we have with the Lyapunov function, right? But anyway, so on the way, we also discussed this very interesting theorem called LaSalle's invariant set theorem, which is a slight extension in some manner, but on the other hand, the base theorem for LaSalle itself is quite powerful, useful beyond proving something is Lyapunov stability, right? It goes back to our the result that says that every positive limit set is going to be non-empty, compact, connected, invariant, right? So we use that. Instead of requiring this v dot quantity to be strictly negative, we can live with v dot less than or equal to 0. Why is that? I mean, many mechanical systems, for example, this is going to be the case. Naturally, we'll get this less than or equal to 0, and then we cannot show asymptotic stability. But in reality, if we apply this invariant set theorem, it's simply one has to look for invariant sets within this set R, which is defined by this v dot being exactly equal to 0. And if the only invariant set within that R is an equilibrium point, we can conclude that we'll have asymptotic stability, sometimes global, right? And if that set does not have a single equilibrium point, you have some kind of limit cycle and things like that. That's also nice to know, right? So in that sense, the LaSalle's invariant set theorem goes beyond standard stability, and in fact it doesn't even require the Lyapunov function candidate, and it can be some bounded function, and then we can still conclude many of these things. Only in the case where we have this v of 0 is 0 and v of x positive, we can actually additionally conclude that the equilibrium point is stable, right? So in that sense, LaSalle's theorem can be used to show boundedness in many cases. And in some cases where everything works out perfectly, we have stability notions also. So we always separate LaSalle's invariant set theorem because there's a gap of 50-60 years between the two results, but from a practical perspective, one should not separate these results. These are kind of one single set of results. You have Lyapunov stability, asymptotic stability, and then invariant set theorem, which is more generic in some cases, but all put together can tell us dynamic behavior of systems. And we will see similar results in slightly more general cases, just see at a later point in this week, right? So how do we connect with all these things with linear systems? Can we actually live with the notions of nonlinear system behavior in the sense of Lyapunov asymptotic and apply it to linear systems? Because in the linear systems we typically are familiar with roots and poles and poles and zeros and things like that. As I indicated earlier, you have transfer functions that can be kind of transformed into state space where you have this x dot equals ax plus bu kind of a thing, and then there's an equivalence, right? So here we are just trying to understand the stability behavior from the definitions that we developed for nonlinear systems, and everything works out perfectly, right? The nice thing about linear systems is we actually have a closed form expression for the solution, and this solution can be computed in many cases using our famous decompositions, diagonal decomposition or Jordan decomposition or any other decomposition that you're familiar with. And the nice thing about Jordan decomposition is each of the blocks of Jordan are going to be having this identity component multiplied by the eigenvalue and the nilpotent, right? And if we didn't have this nilpotent case, then we'll end up with the standard diagonal case. And our behavior of boundedness depends on both of these things, right? And the nice thing, and then we went through some of these details earlier, exponential of any of these blocks times time is going to be the scalar e power lambda I t times e power n I t, where n is the nilpotent matrix, right? What is a nilpotent matrix? When you raise this nilpotent matrix to some power, square, cube or something, at some point it becomes 0, right? And of course, if you make n I power 1 itself is 0, then that's a 0 matrix, right? So if you just pay attention to this e power j I t, if the lambda is such that the e power lambda I t goes to 0, then perfect, this is going to be bounded naturally in the long time. I mean, it's going to convergent in the long time, right? So when can that happen? If the real part of lambda I is going to be negative, right? Because the imaginary part will produce oscillations if they are non-zero, but otherwise the real part will produce the exponential decay behavior if the real part is the negative, right? So in that sense, whatever happens to ni, if the real part is negative, then we are fine. I mean, we'll have a bounded behavior. But if the real part is 0, then this may exhibit either oscillatory behavior or behaves like a constant. So in that particular case, what will happen to this? If ni is 0, then that's going to be identity. So if real part is lambda is 0 and ni is 0, then we'll have a perfectly bounded solution. We may not have a convergent solution. We will not have a convergent solution. We may have oscillatory behavior or a constant behavior, but it will be bounded if ni is 0 and real part is 0. But if real part is 0 and then ni is not 0, what will happen is, it's not difficult to show, this will have an unbounded behavior, right? So that's the kind of the villain, real part of lambda is 0 with ni non-zero is going to give us unstable behavior, unbounded behavior. Okay, so that's the kind of the summary that we can conclude purely out of understanding Jordan decomposition and this matrix exponential, and it is consistent with the notions of nonlinear stability, but much simpler, right? So it goes back to again roots and poles and zeros and things like that, and then some of you may recognize the state space matrix A, the eigenvalues are nothing but the poles of your original transfer function, if you are thinking about these single input, single output systems, right? So anyway, the summarizing, basically 0 of this particular linear ordinary differential equation is globally asymptotically exponentially stable, right? All of them are kind of equivalent. You don't have a local notion separately and global notion in the linear case because they are linear, and asymptotic and exponential are same because all of them will have either exponentially decaying behavior or none, right? If and only if A is Hurwitz, that means the real part of all the eigenvalues are less than 0. As I just discussed at length, basically 0 is bounded with, in this particular case, Lyapunov stable ends up being just simply bounded if and only if either it satisfies the convergence condition, real part of lambda I is less than 0, or in case real part is 0, then we need to have ni equals 0. If any of these things is not satisfied, then we'll have unbounded behavior. For unbounded behavior, if one of the eigenvalues is positive or one of the blocks will satisfy this ni non-zero when real part is 0, then we are done for. Everything else in certain directions you may have perfectly stable behavior, but in other directions we may not. We have seen examples in the previous lecture where on a particular axis you may have actually perfectly convergent behavior, but in every other axis or other point basically they blow up, right? So in that sense, basically instability is far more restrictive in terms of the way we look at it, right? We don't want any kind of bad behavior. So where does this lead us? That's just consistency between our definitions of nonlinear stability to linear stability, and we got these results. But then the nice thing about that is basically we can actually say something about nonlinear systems. Why is that the case? Because if f is well behaved, the function f is well behaved, then basically it can be approximated to a linear part ax plus some nonlinear part, where nonlinear part is very small, close to the equilibrium point, right? So that's kind of coming from your Taylor series kind of approach, right? So I'm going to define this Jacobian matrix, which is simply the derivative of f, gradient of f evaluated at x equals 0. And if that Jacobian matrix A is Hurwitz, then we can conclude that the solution, zero solution of this particular nonlinear ODE is locally exponentially stable, right? We don't get simply asymptotic stability, we actually get exponential stability. And checking for Hurwitzness can be done in multiple ways. One ridiculous way of doing it is actually take the solution e power at and then integrate it out, but nobody does that. But that's also equivalent to actually finding a solution to this particular inequality or even this equality, and there are other inequalities, right? So today I would recommend to use this set of inequalities, quite easy to do using in MATLAB, for example, something called LMI toolbox, and one can check feasibility for these linear matrix inequalities or LMIs, right? So in that sense, we have an ability to show stability or exponential stability in this particular case of a nonlinear system through linearization and simply checking on the computer, right? It's a nice way of doing it. And if it turns out that the eigenvalues, one can check the eigenvalues of A, but the fact that we have these alternative methods of checking the LMIs and things like that are powerful in a separate way. We'll look at that at a later point. But anyway, if eigenvalues have any positive real value, then automatically we can conclude that the zero is unstable. So we have these two extremes. We can show through linear methods, through linearization, one can show either exponential stability or instability, but nothing in between. Unfortunately, one cannot conclude anything about suppose if the linearized system is Lyapunov stable, nothing can be said about the nonlinear system, and even vice versa, right? So so that's the kind of summary of all the results that we have seen, and as you can see, they're quite powerful in analyzing this very complex notion of a solution for a given ordinary differential equation, whose solution is almost impossible to actually derive in an explicit manner, right? Numerically, one can guarantee in certain cases, and you can get approximate solutions, but numerical solutions do not quite apply to checking stability, and this Lyapunov methods are quite powerful in that sense. Thank you.